Good morning or good afternoon or good evening, depending on where and when you're watching this webinar. Uh, my name is Afshin Majd. I am going to speak about Easy Power version 10, comprehensive IEC 60909. So in the version 10 of Easy Power, IEC 909 has been fully implemented. This has to be noted that we did have a version of IEC, so there are a whole lot of new approaches and new methods that have been implemented here. There are a lot of new reports that have been added, and basically what I'm going to go over today is that all these new features that we have added and how to utilize them and how they are going to be used in the areas in the areas and regions of the world whose primary standard is IEC. Of course, IEEE covers and is very dominant in North American countries. Top of that list, of course, US and Canada. You go to other regions of the world, there are other standards, including IEC. It has a older history compared to IEEE, and we just wanted to make the software applicable and something that addresses every single engineer, regardless of what region of the world they work in. So let's start with the first slide. And I'll go over different slides. I prepared them in a way and in a manner that I go back and forth between the slides and Easy Power. I try very hard not to go into details. However, I'm going to cover enough for engineers who like to kind of sometimes check their results or understand the results that come out of Easy Power. That's been consistent. That's been something that if you look at every webinar I have done so far is I truly believe in the idea of being able to reproduce what comes out of a software. So I go and I give you enough details in case you want to go and research the methods. That's also another layer of transparency we're going to provide here. But in the meanwhile, because of the limitations on the time, I won't go into every detail of every single formula in IEC. That's not the purpose of this webinar here. So 60909 had a version 2001. Recently, 2016 version is out. We are compliant with both. I would say that primarily we started the project based on 2001. 2016, I'm going to actually maybe read it off this line here. It adds some material with regard to renewable sources contributions. Formulas have been renumbered. So another thing to keep in mind is that this presentation here, when I refer to the formulas in IEC, these formulas are coming from 2001 version. However, we check them one by one. They're the same. They have not changed in 2016 version, but the number when we reference to them, let's say equation 71, just as a number, it might have become equation 73. That being said, this line is something that I have copied from IEC. It says that covers low voltage, high voltage AC systems 50 or 60 hertz. It happens that IEC dominant, the areas of the world that are complying with IEC, they're mostly working at frequency 50 hertz. US, Canada, we do frequency 60 hertz, but that's the line that comes from IEC, again 50 or 60 hertz. Higher than 550 kV will be subject to a different standard. Let's start with the currents that we have in IEC, and then after this slide, of course, I'll switch to screenshots of Easy Power 10 so that you would see the implementation. That always helps to understand better. So initial current, breaking currents, and steady state currents. We do also provide method, and we have implemented method B, method C, and there is an option called worst case. Initial currents, in case you want to kind of memorize them. So let's just go to the file. In case that you are an old Easy Power user and you have been with us for a long time, you would notice this file is a new file. It's a brand new file. We have added only for the demo purposes and presentation purposes and practice purposes for engineers and countries that are used to IEC numbers. For example, you would see that we have a lot of CDs with secondary of 1 ampere, which everybody knows that it's not a common practice in US. In US, you would see a lot of 5 ampere CDs. Not that there is no 1 ampere CDs, they are, but they are not as common as European or Middle Eastern or those areas. So we tried very hard to reach out to engineers and people who work in those areas to really hear from them and make sure that everything that is implemented here is really compliant and is common practice in those areas. Yet we're really happy to get feedback and hear from you guys if there is anything you think we can implement and make it even better and more convenient for you to use. Again, the purpose of this implementation is really making EasyPower a global software, something that addresses all the engineers all over the world, regardless of what standard you work with. North American countries, you do IEEE, by all means, everything is implemented. If you do IEC, we have gone to every detail and we have tried our best to make sure that we capture all the details there. That being said, you look at this file, which is new. I talked about different currents, so I switched to short circuit, and you would see the initial. You would notice the terminology that has changed here. 1, 2, 3, 4 type of breakings that have been added here, and a steady state. So this one becomes 20 millisecond, 50 millisecond, 100 millisecond, 250 millisecond, and a steady state. You would imagine, and it makes sense, that these are the breaking currents. So this is the initial. You would expect to get the highest value right at the moment of the fault. As time progresses, you would expect, not always, you would expect for some sources the breaking current would show a decay. So let me just go back and forth again here. Initial current, which we looked at it, breaking currents, 4 type of breaking currents, which I talked about, and I have put the equivalent ANSI terminology here for initial versus momentary, for breaking versus 5 cycles. Steady state, there is cycle. Just a way of visualizing how these values translate to each other. Peak currents, we have peak method B, and we have peak method C, and worst case. I'll go through details of them for the sake of this discussion here. Let's take a look. This is the short circuit option dialog page. This is the control option. You would see peak calculation method, by default method C, or you can choose method B, or you can choose worst case. Worst case would look at the bus, perform method B, and perform method C, and picks the worst of these two as the worst case scenario and would display that. Every report that we run, you would see on top of the report, if there is a peak value in that report, you would see whether it was method B or method C on top of the text report that's written. The same for C factor, and in a minute I'll get to C factor, what C factor is, why IEC includes it, what's the importance of C factor, and how EasyPower implements that. So we go back to the presentation here. So we covered these standards here, these new values. C factor. Basically, IEC has a method and a leverage to come up with worst case short circuit current and best worst case scenario short circuit current or fault current, or maximum fault current and minimum fault current. Every standard, regardless of being a IEC or IEEE or other different type of standards, they usually come up with a method to define a range. That's how IEC achieves that objective. IEC, for different voltage levels, as you see, this is a copy from IEC 909, which recommends this C factor. C factor basically is a factor which is going to be multiplied by the nominal voltage. So when you increase this value, you would expect that the short circuit current goes up. If you imagine that V equals ZI, if you increase V by a factor, as you see here, which is larger than 1, of course, in occasions, not always, for CMIN it's a different story, I short circuit current goes up, and that's the purpose IEC is following here, to increase the voltage so that it provides the worst case scenario of the fault current to the user. So, and it has a recommendation for different voltage levels. Let's say from 100 volt to 1000 volt, you see a recommendation of 105. You see voltages larger than 1 kV to 35 kV, which is almost equivalent to what we call medium voltage. They do call it medium voltage. When I say V, I mean North American standards versus IEC. So, this is called also medium voltage in IEC terminology, and high voltage is referred to as voltages higher than 35 kV, and you would see the range for both of them is 1.1. On the other side, Cmean gives you the bottom line. It gives you the lower value of a range in which you're looking at the fault currents. In fact, by implementation of Cmax and Cmean, you would expect to come up with a range whose top value or highest value defines the worst case value for the or highest available fault current, and the lowest value in that range provides us with the minimum short circuit current. Why do we do that? For very obvious reasons. You're looking for rating your equipment. You're looking at your buses. You're looking at the protective devices primarily to find the ratings and see whether or not they can withstand those fault values. That's how you achieve it in IEC, by changing Cmax and Cmean. So let me just put it in a larger context. You would say that Cmax would change parameters in the system so that you would get the maximum fault current. Cmean changes the parameters in a network so that you would get the minimum short circuit current. That doesn't limit the application to only voltage. You would see that Cmax and Cmean and C factor in general, once you choose it, it also impacts some of the factors that are otherwise known as K factors in IEC, and they are important change agents or change parameters or values that can adjust the impedance values, and C factor is going to impact them. So without going to details, you would imagine if I pick C max, I increase the voltage, directly increasing the short circuit current. In the meanwhile, on the other side, I have to decrease, and it should somehow work to minimize the impedance values. What we do in Easy Power, let me bring back Easy Power so that I show you how this C factor is implemented. I go to short circuit option, and these are the C factor implementation for different voltage levels. These are changeable. You can change them. You can put the values here. It's very logical, and it would make sense that your Cmean always has to be lower than Cmax. But number one, impacting the voltage. Number two, I told you, as we discussed, impacting the impedance. Increasing voltage would mean we have to try to minimize the impedance, and impact on the K factors is something which is already implemented, and those are formulas that Easy Power follows. If any K factor has a C value in it, once C value changes, those K factors change, and let's say they're gonna go and change and impact the, let's say, transformer impedances. Some other K values that we define them and use them in, let's say, method B and method C, and all those details there. Those are already implemented. Another factor that we use is that when we use Cmean, we're gonna cut off all the motor contributions. That's one step we take to minimize the short circuit current, and I'll get to that and I'll show that one too. When we use Cmean or Cmax, we will go and change the cables, transmission line impedance values. For Cmax, we try to minimize them. In order to minimize them, we replace them with the value of the impedance of that cable or transmission line at 20 degrees, which makes it minimal. It really lowers it, and we look at the formula for that. When we go to Cmean, we try to maximize the impedance of the cables and transmission lines, which means that we will increase the temperature for those components. So this is where the C factor is implemented, in fact. Going to the next slide. This is a copy of the table 1 in IEC. Breaking currents. We talked about the breaking currents, and Easy Power includes all of them as 909 lays them out. 20 millisecond, 50 millisecond, 100 millisecond, 250 millisecond currents are obtained using mesh network approach. You would go into the terminology of IEC, you would see that approaches at times are dedicated to either mesh network or non-mesh network, and the implementation of breaking currents, we have followed the mesh network approach. We divide the subtransient reactances of generators and synchronous motors by mu. To get breaking reactances, that would be equation 70, page 109, IEC 909, and applies to near to fault machines. Okay, you would see a whole lot of new terminology I use here. Number one, breaking. All these four currents are type of breakings. We saw them on Easy Power screen. Then, if depending, in order to use the initial values, this value, which is the maximum, very much we follow the classical method of implementing and using the impedance, the minimum impedance or the subtransient impedance of the equipment in a Y matrix and calculate the short circuit currents, very much similar to how we do that for momentary current in ANSI or any other classical method that you use. It's just a basic Y matrix implementation with impedance values, I would say subtransient for rotating equipment. And of course, if it's a transformer, the transformer impedance, that doesn't change. The rotating devices are the ones that their impedance changes right after the fault because of their rotating nature. So initial currents, they get calculated very much similar to any other current we do in ANSI, using the impedance values of the devices. If there is a rotating device, we grab the subtransient impedance. Once we go to the breaking currents, we start modifying these impedance values for some of the sources, not all of them. For some of them, we replace this impedance by different impedances. So logically, you would imagine, and let's just run a fault here. If I come here and I run a fault here, three-phase fault, and I start showing the values. Let's say breaking 20 millisecond, breaking 50 millisecond. As you see, the current starts decaying. And it would make sense. That's the initial value. The breaking currents, you would expect them to drop. And again, you see that I'm very cautious using this terminology. That's not always the term. That's not always the case, as you see. If you have a source and you have a stiff source, it doesn't care. It does not decay. It just has the same short circuit value, same contribution over the time. However, that's an entirely different story when you look at the devices like generators, motors, being a synchronous or induction motor or generator, you would expect decay from them. That always is not the case. There might be exceptions. We get to those exceptions. But regardless of that, in order to see how we replace the impedance in those rotating equipment, let's go back to the slide and see what we do. For synchronous machines, so synchronous motors and generators, that's how we modify and adjust the impedance of the initial current. So these values were the values that we use them for initial currents. Then you would think that if there is a source which is supposed to have decay, decay means that the impedance has to go up. So you would look for a mechanism to increase the impedance value of those devices, again, if they are going to have any decay. So I probably don't repeat this term anymore, but you can't expect decay from every single source in your system. If there is a source, and I'll go over all of them in detail, and that source is supposed to have a decay, you have to come up with a mechanism for different breakings so that the impedance values start going up as time progresses, 20 millisecond to 50 millisecond to 100. And that's how Easy Power does that for synchronous machines, synchronous motors and generator impedances. Then by now you would imagine, okay, this has to be a number smaller than 1, and it is. So you divide it by this value, and the result impedance would become higher. In this case, even more, and 250 millisecond should supposedly give you an impedance which is higher than all other impedances up to this point. So this is the story for the synchronous machines, and we changed them. You would ask what this mu number is. That you can go and look at equation 70, page 109 IEC. It's a value that is defined based on how close your synchronous machine to the fault point is. Let me make it very simple. The equipment and rotating equipment, synchronous machines or induction machines which are close to the fault point, they are going to see a sudden change and sudden increase in the fault current once there is a fault. It's very much, if you fault terminals of a machine, you would see a huge increase beginning few cycles, and it dies down as time goes by. That's the trigger that IEC uses to define close to fault or far from the fault machines. So if a machine meets the requirement of being a near to fault machine, then you would see a decay. Being synchronous or being induction, as long as the ratio of the initial current to the nominal current of that machine is higher than a certain value, and that's actually 2 in IEC, but higher than a certain value, then it becomes either a close to fault or far from fault machine. If it's a far from fault machine, it has no decay, and we won't have any decay in there. So in fact, here I'm talking about the sources that have a decay, and those sources, being induction or synchronous, have to be near to fault, and that's how their impedance values get modified. Then you would ask the question that what if it's a far from fault equipment, in fact, which we are not supposed to see any decay? For that case, it's a simple answer. Mu would deliver 1. And if you look at the equations, you would see that they become 1, so the impedance doesn't change. Nothing in that network it changes. Whatever you get for your initial, you would get for all other breakings as well. So far I covered the synchronous machines. Similar story, not identical, but similar story for induction machines, which means that I'm talking about asynchronous, as IEC calls them, motors or generators. We come up with a mechanism to increase their impedance if they fall into the category of near to fault machines. So for 20 millisecond, 50 millisecond, 100 millisecond, 250, I modify and adjust the impedance values based on IEC recommendations, and they go up. They go up as time progresses. And mu and Q, they come from equation 73, page 113, IEC 909, for details. But for the sake of this presentation, you would imagine that if they're going to have a decay, these values have to go up, and as time goes up, these guys have to be increasing. So you would imagine that the mu values becomes smaller and smaller, and mu times Q becomes smaller and smaller as we go up. So this is the essence of these equations, and I hope that I made it as clear as possible without going into too much details. But let's just go back, take a look at easy power again. So for this bus, for example, and this source, you see no decay. Let's take a look at another source. This source does have a decay because it has motors in it. This source does have decay, as you see, and that's the result, that once there are many sources contributing to this point, there is one that has no decay, but there are many others that have a decay. As a result, you would see that the current is coming down. And I can start adding them. Of course, you know that you can add up to 3 parameters, display 3 parameters on easy power, and you will see that these values start changing. So I go to a steady state, and it comes even down. So these 4 are the breakings. This is the initial and a steady state values that I see here. Let me just go back quickly and talk a little bit about Cmax and Cmin. So this is Cmax, and if I go and change this value, let me just do that only for initial so that we can focus on one number. So 18. So Cmax, as I said, a mechanism, leverage, point, parameter IEC defines and allows the user to play with this parameter so that it can come up with the range of the worst case scenario or the highest fault value versus Cmin for lowest fault value. And you can see that here, right? That's just an impact. I'm just trying to give you the leverage and then also clarify how this IEC terminology translates from IEC code to easy power values. And again, I probably try my best not to repeat myself, but it's been a long project, and we literally have gone to every detail of every formula in IEC 909, making sure that every single requirement and recommendation by that standard and beyond that standard is covered. We are really trying hard to make sure that engineers using the software in those areas get exact tool that they need to perform their studies, and that would be an excellent package for North American users to get to know to IEC and details of IEC through this vehicle, Easy Power, And the same vice versa for users in areas that follow IEC, to have a package which provides them with a method to calculate based on IEC, and package which in the meanwhile includes details of ANSI, and they can switch if they want to. So that's the breaking. That's the story about the breaking currents. Let me move on to the second slide. Mu and Q, as I mentioned, are obtained from equations 70 and 73. Only near to the fault machine impedances are modified, as I talked about it. That is determined by checking if the ratio is less greater than 2. And that's a trigger that IEC recommends. That would be a good logical point. If you have a machine whose fault current does not go up twice as much as the rated value if there is a fault, that would be a machine which technically doesn't see much decay. Imagine that would be a machine that would be a generator or a motor which has a lot of impedance between the terminals of the machine and the fault point. Those impedances do not allow the machine to see and contribute directly. Of course it will contribute, but it won't contribute significantly, which in other words, IEC and Easy Power, following IEC rules, considers it as a far from fault machine, and then it's not going to modify the initial impedance values, resulting in seeing no decay from that machine. All other far from generator and motors have their mu and q as 1, and if that's 1, their impedances doesn't change, they're not going to have any decay. After modifying the impedances of generators and motors, the fault currents, bus, and remote branches are obtained from the Y matrix solution, which is a technical, classical approach to solve short circuit networks. The far from fault machines will have no decay, as I mentioned many times so far. That is, initials are equal to breaking, and a steady state in case of motors, the steady states, of course, are 0. I have to spend a little bit of time on this statement here. I just claimed that the short circuit, the steady state motor contributions are 0. So decays, I think we talked about them enough. But let's take a look at, are the motor contributions always really 0? So let me just go back here. I have C factor max here. I have a symmetrical fault, and I have a motor. And I'm going to go and look at the steady state value. Yeah, it looks at the steady state contribution from this source, which was a close. This is a close to fault source because I see decay here. So I turn this one off again, and there is no steady state contribution. Well, understood. Then the rule and exception to this rule is that, number one, that would not be the rule for unbalanced faults. So if you have an unbalanced fault here, and I change it from 3-phase to single line to ground, so I'm going to fault this point and come back and look at the steady state values here for the motors. Let me just fault this point so that I can it's easier to actually focus here, to zoom in here. So, well, I just violated the rule that I set up here. This guy has a steady state contribution. So the addition to that statement is that for balanced faults, we cut off motor contribution for a steady state once Cmax is chosen. If you go and switch to Cmin, and I mentioned it before, you expect to cut off any contribution and try to make the fault current minimum. As part of that effort and approach, we will cut off the motor contribution. So if I say Cmin, you won't see any contribution from the motors regardless. So I go back one more time to Cmax and apply, and okay, it does have a contribution if the fault is one of these 3 type of fault. And if it's a steady state type of fault, yes. If it's a balanced type of fault, yes, the steady state value and contribution becomes 0. So next slide here. This is just a screen capture to visualize what we have discussed so far. As you see, there is a fault here. There is a fault on this bus, and as I switch from 20 millisecond to 100 millisecond to 250 millisecond, you would see that the current starts coming down. This is the faulted bus, and again, if you only had the source, a solid stiff source, it wouldn't be the case. Because we have a lot of motors here, you would see decay. I go to the motors just to examine which one of them is close to fault or near to fault, which one is far from fault. To me, it seems that all of them given the conditions that there, I don't see much impedance, in fact, between the motor terminals and the fault point. They all are decaying, and they're decaying significantly, which means that they're near to fault. So that's the case for the motors here. That's the case for this branch here, which I don't see what component. I would imagine at least it has a motor somewhere down here and a generator here, again decaying. A review and a reminder that rules of IEC for modifying the impedances depends on the type of machine. And when I say machine, machine can be a motor or a generator. If it's a synchronous machine, has certain different rules. If it's a induction or asynchronous machine, motor or generator, it has type of different rules. Now, let's take a look at the peak currents. As I mentioned, let's go back to Easy Power before we forget here. Peak currents are calculated here. These are calculated here, and they're actually, you choose the option here, method B, method C, and worst case. Let's take a look at what method B is, what method C is. Can I generalize that one always provides or gives us higher value versus the other, or it depends? And why did we introduce the worst? Why did we introduce the third option, which is worst case? What Easy Power is doing, this is not coming out of IEC directly, but it's a combination and it's application. That's something that we try to make it easier for you guys to see what's the worst case scenario, what's the highest peak value you can get at a certain bus, certain point, fault point in the system. So and now that we are almost halfway through the presentation, this is not new. Type of fault, you have seen them before in ANSI. This is not necessarily new. This is the very same mechanism that we have in ANSI in order to define the threshold over or under, threshold under, over or under which you would highlight the buses. You know, if the fault, if the value, voltage value drops, let's say below a certain point, or if it goes above a certain point, and we highlight them. This is not a new concept. Of course, the terminology and name of a standard has been replaced here. C factor is new, we talked about it. Value and range of C factor, we talked about it. Braking, as we have 4 types of brakings in IEC, you would go to, let's say, TCCs, you would go to clipping currents in TCCs, and we will refer to a braking current. When it comes to those arrow values, we will refer to braking currents, and you would wonder that what braking current you're referring to. So if you don't choose that braking current in TCCs, and I will cover it either in this presentation or future presentations in much more details, but this is where you choose the braking default as a global option, unless you go and override it in other studies somewhere else, because we have 4 different type of braking. So wherever you see a name of braking, if you didn't override the value, braking 100 millisecond or 0.1 is the one that Easy Power will go and pick. That's for this guy. We are focusing on the peak calculation method, which is method B, method C, and worst case scenario. So I'm going to click OK, go back to my presentation, and continue there. So method B or method C can be chosen as the peak calculation method, which we just saw the screen capture. Additionally, in the Easy Power screen, in fact. Additionally, worst case can be chosen, which automatically picks up the higher current of the 2 methods in display and the report. In IEC, peak currents can also be shown in the one-line display. So this is a screen capture, as you see, and that's where you choose to display them. So if you choose to display the maximum symmetrical value and maximum momentary peak, in fact, it has to be maximum initial peak. That's a terminology coming from ANSI, but that would be a better replacement too. But initial value, initial peak. So the number within the parentheses, as you see, is maximum peak, depending on you choose a method B or method C, and we get to the details of it. The value showing here is the maximum symmetrical value. Let's look at Easy Power. So I go back here, I go to my short circuit options, I go to let's say method B, don't change it, online display, symmetrical values. As you see, all these guys are activated, right? They all are, I can choose them, I can switch between these values. For the symmetrical values, I go and do maximum symmetrical and momentary peak and apply, and OK. And you would see that the initial is on, rest of these values are grayed out. When you're talking about the maximum value, your application is limited to the one symmetrical current, which is providing the highest symmetrical value. That has to be initial, regardless of type of fault, regardless of fault point, regardless of sources that are contributing. That has to be initial. That's why everything else is grayed out. ABC is grayed out because we're looking at the max of those three phases. So you see the options get very limited at this point. But the point is that when I ran that study, maximum symmetrical value, maximum peak value. Let's go back and change a few options, see how they impact the values. I go to control and I'm looking at the maximum peak for method C. What if I do method B? It changed. I switch it back, it changed to a higher value. It seems method C is giving me a higher value. So worst case should give me method C, and it does. So the symmetrical value didn't change when I went back and forth for method B and C. Of course, that comes from initial and it stays there. Method B and C, as you can see, it switches, or if you choose worst case, for every individual bus, we will go look at the method B, method C, pick the worst and display that one. That's a great tool for the users who are, let's say, they're trying to find the rating and proper rating for their buses at this point. That's why we have done it this way, so that you have the excuse me, worst case scenario and you can look at it. So this is a screen capture of the same thing. You can also look at the symmetrical values, which is the default option. You can look at asymmetrical value, which comes directly from IEC definitions. IEC provides a formula for calculation of symmetrical, DC, and then symmetrical squared plus DC squared will give you the asymmetrical squared value, like any other calculation we have learned. So that's a classical way of IEC providing the asymmetrical value. And you can also look at the maximum symmetrical and maximum asymmetrical. So if you see parentheses, what it means is that that value within parentheses is the max asymmetrical, or for this case, max peak value. So I move on to method B. Again, I have tried really hard not to go into details. In the meanwhile, provide enough so that you would know where this method comes from. Method B, obviously, one out of two methods that IEC recommends. Method B is going to look at the bus and all the branches connected to that bus and look at this condition. This is something I have copied. This is a copy from IEC. If R over X and not X over R, if R over X is smaller than 0.3 in all of the connected branches, factor 1.15 isn't used to multiply the peak current. Okay, what it means, this is the formula to calculate the peak method B in IEC. This is our famous initial current. This is a square root of 2. This is a factor IEC defines, and this is a 1.15. So what it's telling us is that this 1.15 is not always part of this peak calculation method. It sometimes is here and sometimes isn't. And if it meets this requirement here, it won't be here. If R over X is smaller than 0.3 in all the connected branches, so if all connected branches to the faulted bus have 0.3 smaller, have R over X smaller than 0.3, 1.15 disappears from here. That's what it says. Otherwise, this is the formula that method B calculates the peak value for a faulted bus. The initial value is sitting here. A square root of 2 is something we always do to get the peak value. KB and 115, at least to me and my experience, are new things here IEC introduces. But it's just a copy of the formula. I don't want to talk about more how IEC has developed these formulas. Method C, excuse me, an equivalent positive sequence impedance of the system is calculated for a 0.4 nominal frequency. In fact, this is a translation that we have used. IEC would go and look at a faulted bus, let's say this point, look at the branches and replaces the frequency for 50, it replaces with 20 hertz, for 60, it replaces with 24 hertz, but basically it keeps a ratio of 0.4. You know, when the frequency changes, resistance value doesn't change. That's the reactive portion of the impedance which is going to change. So by replacing the frequency of, let's say, 60 with 24 hertz, R value remains the same, X value becomes smaller here, and that's what method C does. Replaces the X value for the positive sequence of all these branches with a value which is 0.4 times the original value of X, keeps R the same, combines these values, find equivalent Z, and then multiplies that and then divides that X by 0.4 again. So you would say, what's the point of doing? It seems that at some point this X value gets replaced by 0.4X, and at the end the result and equivalent of the combination of all these impedances, the X value gets divided by 0.4. So let's make it simple. If you had only one branch, not all these things, only one branch, and once you replace the X with 0.4X, and then again you multiply the result by, or you divide the result by 0.4, you would get the X value again. And that's exactly the case. If you have only one branch for method C, you would see that the peak value would be equivalent to the peak value coming from method B most of the cases, and in fact it would be as if you don't even apply any 0.4 factor. That 0.4 factor, which looks like you're doing and undoing something, is effective if you have a combination of more than one branches. If you have only one branch and X gets multiplied by 0.4 and gets divided by 0.4 at the end again, it's as if you haven't done anything with it. And that's really the case for method C. So let me just go back again to the definition and the slide. And that was just the covering of method in IEC. In fact, as I said, this 0.4 is not really 0.4 coming out of IEC. It's this frequency that they recommend to replace. If the system is a 60 hertz system, they recommend it to replace it with 24 hertz. If it's a 50 hertz frequency, recommending to replace it with 20 hertz. But we as engineers know that replacing the frequency in a power system is going to impact the X values, and that's how the IEC also explains it. So once X gets multiplied this value, at the end the result equivalent impedance gets divided by this value. And if you have only one branch, multiplying and then dividing, it's equivalent to not even considering this factor at all. So negative and zero sequence impedance values are not going to change. We don't multiply anything for zero sequence and negative sequence. Peak currents are then found using equation 54, 55, and 59, IEC 60909, which is similar. It's very similar. If you look at those equations, they are very similar to this equation here for method C. So let me, because we talked about these methods, let me just go and run one method C again. Let's say for here, answering to the question which one of these method B or method C consistently provides higher results. I don't know. We don't know. IEC doesn't answer that question, and that's why we introduced the worst case scenario, so that you can just experiment with the software yourself and see which one provides the highest and go with it if that's the case and if you're looking for it. Let me just return everything to the default values. Go back here and take a look at here again. Okay, I need the peak values. So method B, apply the value. Method C, apply the value. So EasyPower takes care of all those changes, even if you didn't quite understand. Of course, you're more than welcome to go to IEC and read the definitions here. Method C to some degrees might look confusing, but I try to make it as simple as possible. For one simple branch, you would notice any change. You don't even need to go through this point for if there is one single branch, because first the impedance gets the X value gets multiplied by 0.4. At the end, IEC recommends that after you find the equivalent impedance for one branch is just that branch. Then you divide the impedance by 0.4. So 0.4 and 0.4 cancel each other out. Again, for one branch, you don't even need to do that. Once you have more than one branch and you multiply the impedance of all branches by 0.4 and you combine them, then the result is going to be different. And for that point, you again have to grab the X value or the imaginary portion of the impedance and divide it by 0.4. That would give you a different result versus if you didn't apply 0.4 to that bus. So the peak currents found using equation 54, 55, and 59, feel free to go and read them. These are fully implemented in Easy Power. If you don't want the details, you can just switch the methods and get the results from the Easy Power and don't even bother looking at the details of the IEC standard. Let's take a look at the steady state currents. For this three-phase fault, as it comes from the name, that would be the current values after a very long time has passed after the fault. So three-phase faults, steady state currents are based on mesh network equations, which are equation 84, 85 in IEC, where motors are neglected in the calculations. One more time, we mentioned this one and we covered it, but I switch back so that we don't forget it. This is a statement that we have to make exception. It's not always the case. If you have an unbalanced type of fault, I'm trying to put everything back to default values. If I have an unbalanced type of fault, the motors will have contribution under Cmax. So let's take a look. This is a balanced type of fault. This is unbalanced, unbalanced, unbalanced. So balanced type of fault, yes, that is true. If I fault this point and I look at the steady state, no motor contribution. You would ask why? It's a steady state and it's IEC recommendation. And in the meanwhile, a long time has passed, the motors has stopped contributing. If it goes to an unbalanced fault though, that's a different story. IEC recommends that do not change the initial, do not change the braking, keep them as they are, and as you would see for unbalanced faults, it doesn't even show a decay. That's IEC recommendation, and a steady state is not cut off, it's there. So that statement, one more time, has an exception. I go back to that statement again. For unbalanced faults, brakings and steady state currents are for unbalanced faults, braking and steady state currents are same as initial currents, which we just saw that motors have contribution to the unbalanced faults, and that is true. Take a look at Cmax and Cmin and what they do beyond modifying the voltage. The first immediate result of applying Cmin and Cmax, of course, is they get multiplied by voltage. So they're going to increase or decrease the voltage. They're going to increase or decrease the fault current. We talked about it the second slide, I would say beginning of the presentation webinar. But here, the default values of Cmax and Cmin can be changed in the short circuit options. Cmin will cut off motor contributions, which we looked at it before. This is where in Easy Power that you can change them. These values are editable. You can change them. You can adjust them. Of course, we have put ranges there. You can just put any value here. Easy Power is smart enough to limit them. It would always make sense that your Cmax is larger than your Cmin. Easy Power considers that logic. But let's take a look at Cmax and what else except for voltage changes. For Cmax, motors are included. For Cmin, they are not. That distinguishes these two methods, pushes this guy more toward minimizing the currents, pushes this Cmax more toward maximizing the fault currents. Cable resistances are considered for 20 degrees. 20 degrees means that we are minimizing the impedance value through which we are trying to maximize the fault current value. So that goes under Cmax. Cable resistances are considered for max temperature, which depends on each equipment. Different for cable versus transmission line, but basically not 20 degrees. It's a value larger than 20 degrees by far, which means that increases the impedance and in turn would contribute to lowering the fault current, because you increase the impedance. After increasing the impedance in a power system, the fault current will come down, and that's an obvious issue for all of us. And this is the formula that IEC recommends to adjust the impedance of the cables, transmission lines. Once you have the value at 20 degrees, at a higher temperature, the R or impedance increases, not necessarily proportionally, but linearly, but temperature goes up and resistance goes up, then fault current comes down and it goes under category of Cmin. Let's move to next option. Text report would require probably 1 hour or even more conversation on this topic. So I just show the text report, and I leave it as an open topic for our future webinars. I just wanted to point out that you would see a whole lot of new reports, a lot of really nice, neat logics that we have implemented in these reports in order to make it very easy for you guys to compare the ratings of the buses, protective devices, relays with the short circuit values. And as you can see, and let me just go back to Easy Power screen here. I go to short circuit option and text report. This one is brand new, almost these two are brand new. We have gone to every single IEC standard in order to include the fuse duties and see for different fuse voltages, low voltage or high voltage, what X over R, test X over R value IEC recommends, and we have included them. We have gone to every IEC MCCB reference standard to see how IEC classifies different molded case circuit breakers and defines different X over R, test X over R for them based on their interrupting capability. And we have included them in our reports. You would see them extremely useful when you go to that reports. And I maybe opened one or two reports, but this is all these options here aren't brand new reports that we are adding here. You would be able to create short circuit steady state report. You would be able to see a comprehensive 909 report, which includes all the breakings, initials, steady state value, and of course equipment duty very much follows the same logic that we had for ANSI, meaning that for each equipment we will go and let's say if there is a fault here for this equipment here, for this breaker here, there would be two scenarios, and that's consistent with our logic all over the system. This is something that really distinguishes Easy Power from other available software packages, that we look at the fault current on the bus and we look at the maximum value if the fault was here and contribution going through this device versus if the fault was right here and the contribution would have been from all these devices going upward. And both of them could be scenarios that create a fault current through the device. We pick the worst of them, the one that provides higher current, and then we start adjusting those values based on device duty. Of course, we go into the conversation of the X over R of the fault point versus test X over R of the device. And again, that's a consistent logic that if the bus X over R is larger than device X over R, then the value that we get out of this mechanism and out of this process has to be modified and has to be increased. If the fault X over R at this point is smaller than test X over R of this equipment here, then that's the point that you can pick the worst of fault for this point or this point and make it go through the process in order to come up with the device duty. Let me just open up one of the reports here. Let's say just not choosing anything here, right? Anything here, and initial HV and LV report, you will see that I checked only one checkbox and I will get two reports for that. Apply, OK, and I run it. Go back here and let me just close everything here one more time. Run it. So making sure nothing else is chosen here. I'm going to look at the detailed report, include branch X over R. Nothing is chosen. Apply. OK. As you see, I checked one checkbox. I have two reports here. One for HV. It mentions what C factor was used. It mentions what pick method was used. And obviously, this is for the HV. The other report is for the low voltage. Bus name, bus KV, symmetrical value for that bus. If that bus is faulted, the fault type is whatever you chose when you faulted the system. X over R ratio for that bus. DC amp comes from a formula in IEC. Asymmetrical value is symmetrical squared plus DC squared is asymmetrical squared. That's very famous. We all know that. A peak amp method C for that bus, and that's the value peak amp. This bus is connected to two branches, C1 and TX2. So that's bus 3. Let's take a look at bus 3. Where is bus 3? Is it this one? This is bus 9. So let me go and look for bus 3. Where is bus 3? Here. So this is bus 3. Let me So bus 3, there is a C1 connected to bus 3, as I can see, and there is a TX2. Of course, this is bus 3, and branch name is C1, and TX2. This is TX2, and this is C1 connected to here, both of them. They have their own X over R. These are X over R for those branches. Symmetrical amp value through this branch, symmetrical amp value through and these are initial values through this branch values that you see. So for this guy, I'm getting 179.54 if I have a fault here. I'm gonna turn everything else off. 179.54, 17.802, and 156, and you see the values here coming, and they are exactly shown here. So this is the report for the high voltage, and very brief. I go to other report here, which is for the low voltage. Again, the maximum C factor is given, peak value is method C. Every detail is laid out here. These reports are excellent source of information once it comes to really analyzing your system. We have tried to cover every possible angle, every possible value that you might literally need in terms of when you perform a study. So these reports, I would say that hardly you would find any report or anything that is missing from this combination. And again, a lot of them are new. That's why I said the best would be we dedicate probably 1 hour at least conversation on the reports, how these values are calculated, the duty values are calculated, and we will cover them. Let me also take a look at the comprehensive 909, which very much covers all different values that you need. And short circuit report for different buses, symmetrical, X over R, peak value. This is braking 20, braking 50 millisecond, braking 100 millisecond, braking 250, and a steady state for all buses and branches, and it goes on. So this is very much a capture, high level capture of IEC. So that's the discussion of the reports that we have added. So a lot of reports have been added there. Let me go to the next slide. Phase shift conversion. This is new feature we have added because IEC uses a clock number notation system to classify the phase shift in transformers. So phase shift of 30 degrees, 90 degrees, 150, 210, 270, and 330, which are all available, all recommended options in IEC, they all have been added here. 13579, of course, multiply each of them by 30 degrees, and that would give you these numbers. As you IEC engineers would very intimately know that knowledge. That translates to these values for transformers. As I said, this is a new feature in IEC. You can use it. You probably won't see the extent of the work that has been done behind the scene to include this feature, but this is a big feature we have included here, and it is going to shift the positive sequence components. It's going in this direction, in positive direction, and it's gonna, let's say if you have 30 degrees phase shift, your positive sequence value is gonna be shifted 30 degrees, your negative sequence value is gonna be shifted minus 30 degrees, and of course zero sequence doesn't make it through the transformers which have this type of phase shift. So let's take a look, see how it works. I'm going to go to short circuit option. I'm going to go to control, one line output, and see, okay, I want to see magnitude and angles for this case. So I click apply, come here, look at this transformer, see if this has a phase shift. Yes, it does. 11. The reference always would be the HV side, and we show the HV side. The HV side is always according to IEC recommendation shown in capital letters. So D capital, Y lowercase, N, for example, 5 would means delta high voltage, Y low voltage, phase shift 150 degrees, and Y grounded transformer. That's what it means. So I go back here, I look at the values. This guy is minus 75, and I'm going to look at it's a three-phase fault. So positive sequence. So the positive sequence minus 75, it goes to the other side and it becomes minus 83. Phase shift again was 30 degrees. So I increase this one. Okay, minus 71. And this, if you notice, in fact, let me fault somewhere that would make our calculation a little bit easier. Maybe I can fault here. That would probably make it a little bit easier for us. Okay, and I removed values. Okay, so that makes it easier because both arrows are in the same direction. Minus 75, 30 degrees, minus 105. This is not a type of fault that produces negative sequence, but if you have a fault, let's say a single line to ground at this point, then you can look at also positive and negative sequence, and you would see that, for example, this guy is minus 75, minus 75, and the phase shifts are different on the other side. One of them is 30 degrees, and the other one is minus 30 degrees, in fact, because the direction of the arrow changes. So we have to first rotate the direction of arrow and then make the comparison. But basically, bottom line is that if you have a fault here and it has a zero sequence, it has a positive, negative, and zero sequence value. Zero sequence wouldn't make it through this transformer. That's number one. So as you see, you have zero sequence here, it wouldn't make it through here, becomes zero here. Your positive sequence is going to be shifted 30 degrees, 30 degrees according to this clock notation number, and your negative sequence is going to be shifted minus 30 degrees, which you can just calculate here. So that's a brand new feature included in the system, and has been fully tested and fully functional, can be used in systems that you use. Database report one-line display uses capital letters to denote the HV side, and LV side is denoted by lowercase letters. So HV side always uppercase, and LV side lowercase. EasyPower compares from and to sides to specify which side is the reference. As I said, HV according to IEC definition is the reference. In case of both sides having, this is a great exception to keep in mind. In case of both sides having equal voltage, EasyPower assumes from side to be the reference. Applicable only to dy transformers. That's very obvious. If you have a yy transformer, you don't expect to have any. So I say no, come back here, go here, and if I have a yy, there is no clock notation number. I mean, it doesn't make sense to have a phase shift here. So and this disappears. So it applies to dy applications. For a 30 degrees phase shift, positive sequence is rotated plus 30 degrees, negative sequence is minus 30 degrees. Zero sequence current won't flow because the path is broken. Transformer phase shift is here. We already saw that. We used it, and it's a very, very powerful, useful tool when your transformer has phase shifts. We have included a new damage curve, IEC damage curve, IEC 76 5.4, which you can find here, and you can use it for IEC users. We get to the point that we talk about the IEC example file. I briefly touched on this topic. Let me just add a little bit more. There are two brand new IEC files that you can use. I would highly recommend that if you're demoing IEC to a user, or if you are a user and you're using IEC or new, I would highly recommend to experiment with this file. Everything has been taken care of for you. CT ratios, combinations, transformer phase shifts, voltage levels. We have gone to a level to run it by 4 or 5 of experts in the countries which are IEC dominant to give us the voltage level common in those standards and those countries. And I'm really hoping that we address all IEC users all over the world. And again, feel free to reach out to us and give us your feedback. We'll be happy to implement that so that we make sure we have addressed every IEC user all over the world. So voltage levels are adjusted, CT ratios are adjusted, transformer shifts are adjusted. This is one file that is new here, and the second one is and the second file is, you go to sample folder and you will see that the IEC 609, this is example 6 of IEC file, from which we have developed this file here. This is basically just to prove the point that how strong, how good, and how well developed this engine works. We have matched every single result, which in few slides from this point, I'll show you how EasyPower matches the results with IEC example 6 and how close the numbers are up to second decimal point, all are 0. So I can claim that we have matched perfectly the results. And IEC has been, this is the step that we have taken proactively to assure all our users that the results are applicable. They can make sure that everything that IEC recommends has been fully implemented. This is not just one method or two methods, it's a full implementation of IEC, and the results are all in line with what IEC recommends. So this is the second new file that we have added here. As you can see, for demo purposes, the best would be the file that I just showed you to use it, because that one has all the values ready to go for you to come and use it. You can run TCCs, you can run reports, which I will talk about them in the future presentations. Everything is ready to go. The second file is IEC file. We just put it in there to prove a point, to make a point that everything is, or you don't need to double check the method. We already did it for you, and we have the results, and we release them, and they are in this presentation that you will, just a minute from now, you will see that. Results of example 6 from IEC 6094 2001 can be verified by the same sample file attached. Feel free to verify them yourself. Otherwise, I'll show the results to you. So IEC short circuit HV, this is the report we have used. This is a copy, untouched copy from the table 12 IEC 909, this one 4. So easy power results, IEC results, and bus 1, bus 2, bus 3, as you see the values, we have matched all of them. Peak values, method B here, peak value method C, next slide here. So this is IEC report. Feel free to run it yourself. Feel free to do the screen capture yourself, and you see how closely they match. They match perfectly. Not to talk about the easy power necessarily, the details and the extent of this work, but as I said, this is not just one method or two methods. This is a combination of a lot of approaches we have implemented there, and that's really significant that so well these results are matching here. Steady state report values, compare them with what IEC recommends, example 6. HV breaking values, C factor 1.1, and the asymmetrical, symmetrical values, the breaking values here. The same report, HV initial report, C factor 1.1, peak method C, peak method C, and the values get compared here. Initial, peak. So initial and peak. In terms of the number of devices, so we are getting close to final slides of this presentation. We have added closer to 2100 IEC devices. These IEC devices is a result of our work with many representatives, many engineering and experts from different countries in the world, European, some Middle Eastern, Chinese. I can just name many different countries that we have gone to those experts, we have asked for those devices, and we have added them to our library. We have done, again, everything possible to reach out to a global audience, make sure every voice and every opinion has been implemented and has been addressed, and still we are open, and we will be more than happy to get feedback, making sure this software becomes something that has application all over the world. 2100 IEC devices are added. Same time, 2300 ANSI devices were added. Of course, ANSI has been around for a long while. Us being in North America, it's much easier to add those devices. I just wanted to make a comparison that how much effort we have made to reach out to other users, other points, other regions, and add IEC devices. Any IEC device which has a data sheet and you feel it's missing from our library, please submit it to us. We will add it at no cost. We have added new terminology, boxes, parameters for IEC devices. So some of the protective devices, you would see that their editor page has changed. That's in order to make sure that we are compliant and we can accommodate parameters that IEC defines for those equipment. For our library, this is not the latest, actually, at least it's not as of today. It has this information are like almost 4 or 5 months old now, but ANSI devices 2227 and IEC devices 2072. Just a point of addition, like these are additions. This is not a final count. This is addition from the time that we have started the effort of adding devices to our library, and it's ongoing, and this is not the latest. It has significantly gone up. I just wanted to make a point that we have made it a parallel effort with ANSI. We have made the point that for almost every single ANSI device that we have added, we wanted to make sure that there is IEC device equivalent added to our library, so our library is, again, addressing everybody. In summary, just to close the conversation here, this module and additions are really far beyond just 1 hour or maybe slightly more than 1 hour that I've been talking for this presentation. We will continue with details of the report, details of the calculations, and more on IEC topic. Please feel free to reach out to us, give us your feedback. I hope that this really covers a whole lot of topics, makes IEC a useful tool if you use IEC in your calculations. We covered comprehensive implementation of 909 standard. I talked about addition of a few new features, including transformer phase shift, clock number notation, that's right out of IEC 60076.1. Providing a standard-based symbols. If you notice, you can switch back and forth symbols. Maybe I didn't talk much about it. There has been webinars on that topic, but you can always go to tools, options, option dialog, and you can go to symbols and change them. IEC, ANSI, and you see they change. That's again one more step we took to make sure that it's convenient and your eyes are familiar with the symbols that you see if you're using it for IEC or ANSI. Several new reports of IEC. It will be upcoming webinar with details on that one. Addition of IEC protective devices to the library, talked about that. Customizing 2 files following all common practices in IEC compliant regions of the world, which I talked about both new files that we have added. IEC example file is the one you can use for demo purposes, and 909 file is the one which is copy of example 6 IEC. That was again a point to show that you do not need to worry about the precision and the calculation at all. If we match these results in these big tables up to the second decimal point, I don't see any concern. I don't see any reason for any IEC user to be concerned about this method. That's just the assurance for you guys that the method have been well tested, have gone through many cycle of QA, and hopefully that should address all the needs in those regions. That being said, I just wanted to kind of conclude this presentation. I hope you have enjoyed it. I really appreciate the patience, and I look forward to your comments. I hope we find a lot of IEC users and North American users who are interested in learning more about IEC, and again, Easy Power becomes a global tool. Thank you very much. Have a good day.